Yeah, so these are the exercises I would like to work on. Some of them we've already done for about 90%. First one, typically. The second one, I've actually claimed that was the case, although I haven't explicitly showed it to you yet. You can write the Lorentz transform as this. The whole transformation. Before, what we did, we showed that A mu is a 4-vector. I gave you the argumentation for this. There's a second way of proving this, and this is what is going to be explored in this exercise. What I would like to do with this exercise is take these two equations, these. I've written as one big equation, that's this one, right? For alpha 0, you get this one. And for alpha 1, 2, 3, you get this one, that. And what I would like to do is just do the Lorentz transform. Actually do the Lorentz transform on the x's and the j's, and then show that this thing must indeed itself transform as a Lorentz transform. I've given you a quick argument before the break. This is a more elaborate argument, but leads to the same conclusion. Just do it explicitly. Now, here's the exercise where the geometric interpretation is of Lorentz transforming your vector potential and scalar potential. Because if you have your scalar potential and your vector potential, you can calculate your E field and your B field. Now we know how this one transforms and how this one transforms. We've proven that they do it under Lorentz transforms. But that means that if you Lorentz transform this equation, you should get back how the electric field in the other guy's coordinate system looks. And if you Lorentz transform this one, you should get back how the magnetic field in the other guy's frame looks like. And the question then is, what are these rules? How do they transform? How do the E fields and B fields transform? We know how the A field and the phi field transforms. How do the E fields and B fields transform? Now, these I just added on the spot just a second ago, just for funsies. Remember that last week I wanted to show you that a contraction of two things is invariant. And I started with a notation, and the notation was bigger than my point. Now that we know the notation, here's the shorter version, the one that I wanted to do last week. To do so, Chai and I already talked about this in my office. First show that this is the case, where these are Lorentz transforms. Note there's a number of contractions here, you have to check very carefully. And once you know that this is the case, then show that this contraction, here are our good friends V and W again, that this contraction is the same as this contraction with the primes. In other words, that this is invariant. One thing we already know, but now in 4-vector notation. Now, tomorrow, I think a couple of these certainly we can do today. Tomorrow, I'd like to show you something about the Maxwell stress tensor in the form of an exercise, but no point in telling you the exercise today. So how should we do this? Age-old question. Work on this yourselves for a while, do them step by step, or... Well, yeah, let's do that. Yeah. Which one?
What is that supposed to be?
Oh, by that I mean the project of you trying it first, and then see what we got. Okay, so I think that first one should only take a couple of minutes. The second one a little bit more, so shall we say 10 minutes, 15 or so? Yeah. Question fully understood. Let's just do it with a group of us. For the people who are interested, I've really just summarized relativistic electrodynamics now. All of it. That's here. Because we saw that these two equations that give you this vector potential and scalar potential can all be written as this one equation, where now the 4-vector of the potential and the 4-vector of the charges and the currents all are combined into this one equation. So solve this one. So you get your phi, your A0 if you will, and your vector potential, that's A1, 2, 3. Solve this from this. Once you have your phi's and your vector potentials, plug them in here, and you have all of electrodynamics. That's all. This is everything that we've done in 3 equations. So that's nice. Tomorrow, we're going to formalize this into 1 equation. But that's tomorrow. So this really just summarizes everything. Tomorrow, squeeze it even into 1 equation. 1 big relativistic equation that contains all of relativistic electrodynamics. So that's nice. No new physics, by the way. It's everything that we already know, just more and more relativistically put. Okay, let's go. Show that such and such and such is, that this really is a shorthand notation for this whole thing. In other words, this is just an exercise in practice of the notation. Did anyone have difficulty with that one, the first one? No? Because if not, I suggest we skip it. It's very much the same as I showed you before. The dx mu with the Minkowski metric in front just gives you the Minkowski line element, yes? Okay, so I suppose we skip that one. Now, show that such and such constitutes the Lorentz transformations. All right. Well, let's just write them down. This is the claim. There you go. Do you remember what the Lorentz transform were in non-4-vector notation?
dt prime equals gamma.
Yeah. This one, yeah?
Yeah.
Okay. So. There you go. And the inverse is just swap the primes with the non-primes and put a plus in front of where there are now minuses. Okay. So the question is, does this really give you just back that? Now, note, mentioned this before, these are 4 equations. Mu0 is 1 equation, mu1 is 1 equation, mu2 and mu3. And then this side, because there's a contraction in the nu, not in the mu, right? For a contraction to do the summation, you have to have 2 mu's on one side. There's only 1 here, but there are 2 nu's, so there's a contraction in nu. And because nu can have 0, 1, 2, 3, 4, 0, 1, 2, 3, this is 4 terms. That's what I said before. These are 4 equations. For every mu there's 1 equation, and each of these has 4 terms because of the mu's. Now let's just write them out. Mu is 0. That's one of these 4. Equals 0, right? Mu I put a 0. So that's this. Now dx0 is what we call dt. So this is really just dt primed. So there's that. What should we do now?
Apply the matrix.
Apply matrix. I agree. The matrix I wrote down there-ish, but let me just rewrite it here. Gamma minus gamma v minus gamma v gamma 0 0 0 0 0 0 1 0 0 0 0 1. There you go. Well, let's just apply it. According to our contraction, this notation, we have to take mu, each of the 4 values, 0, 1, 2, 3, get 4 contributions, add them together. So, fortunately, this is short enough that we can actually write it out. So, nu is 0 times dx with mu0, which is this one, plus 0, 1 dx1 plus 0, 2 dx2 plus. Okay, this is writing out the new contraction. And now we just read out the values. Because this thing tells you the mu. Remember that? It tells you the row. This one tells you the column. So what we have here is take the 0th row and the 0th column, take that number, which is gamma. So this is gamma. Now dx0 is what we call dt. Let's continue. 0, 1. So 0th row, first column. zeroth row, first column, minus gamma v. dx1 is what we call dx. Let's continue here. Zeroth column, excuse me, zeroth row, second column. That's 0. So that's plus 0 times dx2. dx2 is what we call dy. And 0, 3, 0th row, third column is another 0. 0 times dz. And if you clean up a little bit, you get this. Which is indeed is the correct Lorentz transform. Alright? So we've checked that this indeed constitutes this Lorentz transform, but there's 3 more we have to do. So this was from u is 0. Let's do this from u is 1. I think we can be quick about this, yes? Apply the same trick. So that gives you dx1 prime. Crappy notation, my 1 and my prime look the same. Okay, according to this, mu is now become 1. There's still a new contraction, so there's that. Just applying the exact same steps now. This gives us gamma lambda this, dx0 plus this is having written out the mu contraction. And now we read off the numbers. Let's see. First row, 0th column. First row, 0th column.
Minus gamma
Minus
v.
gamma v.
Thank you, thank you, thank you. Just checking if everybody's still there. dx0 is dt, yes? Okay, plus 0, first row, first column, gamma. Okay, times dx1, which we call dx confusingly. First row, second column. 0 times dx2, which is y. And first row, third column is another 0 times dx3, which we call dz. Clean everything up. Gamma dx minus v dt, which indeed is that Lorentz transform, the dx prime one. So that's good. This beautiful shorthand expression here has given us 2 of the 3 of the 4 Lorentz transforms. Let's see if the other one also holds. Mu is 2. dx primed 2 should be, according to our formula, Lorentz matrix 2 mu dx mu. Just substitute the mu as 2. Write out the mu's, the contraction. This is me writing out the contraction in the mu's. And now we read off the values for the Lorentz matrix. 2, 0. Second row, 0th column.
0.
0 times dt, that's right. 0. This one, d1. So 1 times dy, and this one is 0 again, yes? In other words, this is what we call dy primed, and that's indeed is the correct Lorentz transform. Same for dz. So, this beautiful, beautiful expression here is all the Lorentz transforms that there is in the universe. So that's good. So that's the first tip. Feel like doing this together? Yeah. Okay, so here's what I suggested. that you take this equation, then you Lorentz transform into some other guy's frame. Means that everything gets a prime. Not the Minkowski metric, by the way. That's just numbers, minuses, pluses, and such, zeros. So if you do this, now I know how this transforms. I also know how these transform a piece. You might remember that a derivative transforms as a 4-vector. I haven't proven this. It's a step that I would like you to think about for tomorrow, why that is the case. But I told you we're going to take it as a fact. This transforms as a 4-vector, but here that was the rub, as a contravariant 4-vector. It goes by inverse Lorentz transform. So, given that that is the case, can you fill me in what this should be? You know what? We can do this. We can just do it with the Lorentz matrix. That was your suggestion. Let's make life a little bit more easy for ourselves. Okay? It's not wrong doing it by Lorentz transform with the Lorentz matrix as such, but let's just make life a little bit more simple. Suppose that you have these two observers and they move with respect to each other in x direction. Then we're just going to write this out for a second, just back in its original form. Now you might recall that was just this. Please check that you understand what I'm doing here. There's a prime here, prime there, and a prime there. This whole thing, including the Minkowski, it was really just shorthand for this. Remember this, right? So I think I'm going to do this in the written out way because it's much more clear. For the newly initiated, this is probably the best way to do it right now. Okay. Now if you have two observers moving with respect to each other in x direction, how do the y and z directions change? The y and z components? Not at all, right? So that means that a derivative with respect to y primed is really just a derivative with respect to y. The y's have not changed if the two observers are in x direction moving with respect to each other. So might as well write this as dy, second derivative, and this same argument for this z's. So I've dropped the y's here because they don't change anyway. But how do these change? The t's and the x's. Do you recall? Do you remember?
Yes, over there, right?
These? Oh, yeah, that one.
Yeah.
Ah, be careful. Those are the dx mu's.
Plus.
Yes, exactly.
Wait, can you say that again?
Yes. These two is dx mu, and those are transformed via Lorentz transform. But what we have here are not dx mu's, derivatives of these.
Yes.
And those transform with a plus sign, with the inverse Lorentz transform. Okay, so let's do that. So what we have here, I'm just going to take this piece and write it out just to see what you will get. Agreed? Second derivative is just one derivative and then another derivative. Now let's start with the derivative here. One, oh, there should be primes, excuse me. There you go. There you go. This one we know how it transforms on the Lorentz transformations. Namely, via inverse Lorentz transform. That was that rub. So, what is the inverse Lorentz transform of this thing? I'm going to write something here. That is a replacement of this ddt primed derivative.
It's gamma ddt plus v ddx.
That is exactly right. Remember, this thing is a 4-vector, so it goes via Lorentz transform. It goes via inverse Lorentz transform. That's exactly what Stephanie just suggested. It's exactly this transformation rule, but with a plus sign. Okay. Now, we're going to look at the situation where the two observers are moving with respect to each other with constant velocity. So we're going to take v as a constant. There's a reason for this. Because we want to be able to apply special relativity to both observers. And you cannot have that one of them is in an inertial frame, and the other one also has to be in an inertial frame, so there's no acceleration between the two. So that means that v must be a constant. But that means that this ddt will not feel the gamma. It will also not feel the v. Gamma is a function of v, but v is a constant, so gamma is a constant. So that means all these derivatives do not feel the gamma or the v. Agreed? So that means as far as these derivatives are concerned, you would get something like this. Be extremely careful here with the primes now, but this is correct. Some I've t's and x's I've Lorentz transformed to non-primes, and there's still one to go.
Sorry, why is v? Sorry, how did you get there again?
I just took this derivative of this whole thing,
Right.
but I took gamma and this v as constant, so they get in front of the derivatives.
All right.
And the reason for that is that the two observers are moving with constant velocity with respect to each other. And then you get this, just from the product rule of differentiation. Not the product rule, just the fact that the sum of two differentiations is the differentiation of the sum. Okay, but we still have to inverse Lorentz transform these. Yes? Now, fortunately, you already know how to do this. We just did it. Replace this ddt by this difficult part here. We can do the same thing with this ddt. So I'm going to replace this ddt primed with its Lorentz transform. So, which is again this. What I've done now, I've taken this one and I've Lorentz transformed this one. It gives me this in full. I also have to do it here. Gamma, this gamma gives you gamma squared times v. Okay. Then there is this one, this derivative with a prime, I replace with its Lorentz transform, but again, inverse Lorentz transform, that's that same rub again. The derivatives go with inverse Lorentz transforms, plus v dx dx. So you get this. It's a lot of work, isn't it? I like a previous argument better.
Sorry, where did you get gamma squared again?
That is, I was a little bit too quick. Yeah, excuse me. Should be no gamma. Should be L squared. This is correct.
Oh, you have another one inside. Okay.
Yeah.
Yeah.
Yeah, I originally wanted to take these together, but I just messed up my brackets. But this is correct, I think. Man, that's a crappy expression. Yeah. Maybe we can clean up a little bit. That would be nice. Because what I see here is two derivatives with respect to t. Yes? this one and that one gives two derivatives with respect to t of this thing, and it gives you a gamma squared in front. So I'm just grouping together everything that gives with the second derivative with respect to t. Okay, any more? Am I missing something here? I think this is correct.
Yeah.
Okay, good. So that's this one, these two together. I also see a second derivative with respect to x here. And that one comes with a gamma squared v squared.
Where did v squared come from? Oh, sorry, I didn't see it. Yeah, yeah. Okay, got it.
Anything else? Well, and then there's a derivative with respect to x and there's with respect to t still. And I think those look exactly the same. dx dt with one v and a gamma squared. And that's the same here. So I get 2 times gamma v ddt dx. I get this. And it's a long expression, isn't it? Man. So what have we done now? I've just taken this thing and Lorentz transformed it to the other guy's frame. So this whole thing, the left-hand side of our equation has now been rewritten. Now I know how to rewrite right-hand side because I know that this is a Lorentz, a 4-factor. Oh, no. We still have to do this one. God, life sucks. Yeah, I'm sorry, I just had this one. Right. Again, note how easy life is if you don't have to worry about all the contractions, to writing it out. Oh. You will hate me in a moment when I...
But isn't it just going to be basically the same thing?
yeah, but there might be some difference though. But maybe you're right. Maybe we can... It's going to be very similar. I very much agree with that. Can we already see what it's going to be?
It is going to be pretty much the same thing. Just this time the v squared is on the time of dt.
Okay, just tell me what it is then.
So gamma squared, v squared, and then v squared
Which derivative this is?
t squared.
T.
Yep.
And next?
And then plus gamma squared again.
Yeah, and then without the v squared, yes?
Yeah, without v squared.
Great. Now, for the people who are not seeing this immediately, it's really just the same series of steps. And you get this again.
Shouldn't it be gamma squared over there?
Where?
Well,
This
gamma
one?
Yeah, 2 gamma v.
Well, you're probably right. It's not going to matter much anyway, if you already see why that is. But let's be very strict here. This gamma is the gamma squared, you're right. But I'm not going to care about that one as much anyway. I hope you can already see why. Because I have this one, this whole expression, with a minus sign. And I have this whole expression with a plus sign. They both have this, but one comes with a minus, the other comes with a plus. They cancel each other out. So if you take these two together, which I'm going to write down here, so I'm just going to plug in this thing that we derived here with a minus sign, and then this thing that we derived here with a plus sign. These have already cancelled out. Just going to see what we end up with. What I see is minus gamma squared dt squared plus gamma squared v squared So that's this one. Again, I'm ignoring this one because I know it's going to cancel out. Oh, there should be a minus here, of course. That's this minus. And then I'm going to add to this, I'm going to add this. All right, let's add that. That's this thing. Plus gamma b squared b squared plus gamma squared. Agreed? So that's these two. Now, these are very simple. In fact, I'm going to ignore them from now on. Because all of our physics is going to be in the x and t's. If you want, you can add them and you can see that they don't contribute. For lack of space, I will ignore them from now on. Let's clean up a little bit. No physics, just mathematics. I see here a ddt, well there should be no prime here, excuse me. I see here ddt squared, here ddt squared. One comes with a gamma, the other comes minus gamma, the other comes with a gamma squared v squared. Let's clean everything up. What I've written down now is this one and that one grouped together. And I can also group these two together because both come with a second derivative with respect to x. Get this. This is me cleaning up. Sorry?
Stuff cancels out.
Yeah, but what?
The gamma squared and the 1 minus v squared.
Yes.
Because we set our c to 1.
Yes, yeah, exactly. The gamma, yeah, exactly. Gamma is 1 over the square root of 1 minus.
So squared and then.
Yeah, exactly. So these two, yes, again, the c's are put to 1, yes? So don't worry about the c's. This together is just 1. So I get minus second derivative. Same here, same argument. I get this. Huh. Isn't that interesting? Look, we started here. Derivatives, second derivatives with the primes. And I get the exact same expression with back derivatives without the primes. Surprising?
Not really.
No,
Why?
Because they're invariant.
Sorry?
Because they're invariant.
Not the derivatives, a piece.
Oh,
But this was a contraction. And we have proven last week that the contraction of two four factors is always an invariant. So we just see that explicitly here again. So you could easily just replace all the primes here with the non-primes over there that we've explicitly shown now. Are we close to our solution yet now? Well, this part we have now fully rewritten in terms of the non-prime coordinates. How about the right-hand side? Right? We have left-hand side, rewrite, equals the right-hand side, but the right-hand side comes with a prime. I also want to write that as a non-prime thing. How do I do that? Lorentz. Inverse or normal?
Normal.
Normal, exactly. So what is that expression? This one?
So for conference 0, it's a comma, brackets, J0 minus BJ1.
Yes. Now J0 is what we call rho. There we go. Now what have we done now? We have rewritten our equation as seen by one observer almost completely in terms of how the other observer sees it, except these primes. Those we have not removed yet. All the other primes are gone. Now the question was, show that in order to make this work, these A primes have to be related to the non-primes via Lorentz transform? That was the question. I'm going to erase this because I'm going to continue over there. So again, what we've done, we've taken an equation that we know that holds in some guy's Lorentz frame, transferred it to some other guy's Lorentz frame, we get this. Let me write it here, just for convenience and overview. Equals minus gamma rho minus V1. All the primes we have removed by Lorentz transforms, except for the A primes.
What about the Lorentz transform for with the second equation part?
What second equation?
Like the one we have for dx. Is that no?
Yeah, wait.
The second component of the J.
Yeah, the
Oh.
second
J
component.
mu.
That's-
Oh yeah, no, oh yeah, oh yeah, oh you're very right. Yes. Yeah, of course. Yeah, thank you. There was an oversight of mine. You're right. We took this thing and then we Lorentz transformed it like this. But it's only true if if alpha was 0, right? That's the only way that this one appears. So by writing this one as this, we've assumed that alpha is the 0 one. So let's continue with alpha 0. Yes? Okay, now my question now was, show that alpha 0 primed is related to non-alpha 0 by Lorentz transform. How about this? Let's assume that they are related in that way. So let's assume that alpha prime 0 is related to alpha non-prime via Lorentz transform. So this is an assumption. If that assumption is correct, then substituting this into that should give you an equation that is correct. Take a moment to parse that line of reasoning. Starting with this, we know that this is correct. We applied Lorentz transforms, which we know are correct. We got something in which there's still A primes. In order to show that A primed and A are related by Lorentz transform, I assume that they are. I plug it into the thing that I know is otherwise correct. If the thing that I end up with is still correct, then my assumption was correct. That's the reasoning. So let's assume that this is the case, an assumption. Let's plug it in. If what I end up with is correct, then I know that this assumption was valid. And then I know that apparently A really does transform like a Lorentz transform. Okay? That's the idea. It's now a matter of just plugging in, doing the math. Minus this one, A prime 0. Just substitute this. Same here. Gamma A 0 minus A1. I've put it in. If this is correct, then I know my assumption was correct and I know my A is transformed like a Lorentz. DDTs, do they feel the gammas?
No.
No. Right. So this one. Do they feel the V's?
Yes.
I hear yes. I see some people shaking their heads. I see some yeses and some no's. Well, do they or don't they? What is V?
Well, V is dx over dt.
Sorry, is?
Yeah, it's a time derivative of your distance.
That is true. But is that a constant number, that time derivative? Is V a constant?
Oh wait, yeah, it is in this case.
Yes.
Yeah.
So that means that this ddt will not fill that number. And it also did never felt gamma. So the gammas and the v just fly through the derivatives. So I get this. Same argument applies here. Now gamma certainly does not depend on x, and v does not depend on x. So this here too, the derivative does not feel the gammas. Question mark, because this is what we have to show, that this is still true. If so, our assumption is correct and the A is transformed as a Lorentz. Do we make any sense out of this? Can we show that this is the case? We have to show that this really is that. If so, assumption is correct. Let's replace the A zeros by phi's. Okay. Huh. I don't know what that means.
It's going to be
Just following your suggestion. Let's see what happens. He says group all the phi's together. Okay. Now this phi comes with a second derivative and a minus gamma. Okay. So that's this one. Here's another one with the gamma in front. They have an overall minus sign, yes, so that's that. Grouped all the phi's together. Yeah, of course. You already see what's happening, yes? Okay. Jair's already seeing it. Let's do the same with the A's, the A1s. I see an A1 and a V, gamma V dt. Please feel free to check me. Do not make mistakes. Do you see that the whole left-hand side can be written as such? No physics, it's just regrouping of the terms. All the phi's are put together between brackets, all the a's are put together between brackets. Equals minus gamma rho plus gamma v j1. Is this true? Remember, we're still checking whether this is true. What is this? A second derivative of phi with a minus sign with respect to time, plus a second derivative with respect to x with a plus sign. Sorry?
It's rho.
Rho or minus rho? Which one is it?
It's minus rho.
It's minus rho.
That's from the other equation.
Yes. If you recall from electrodynamics, the phi's obey the differential equation that two derivatives with respect to time with a minus plus two derivatives with respect to x equals minus rho. And this equals minus j. These are just the differential equations we derived a couple of lectures ago. So ultimately, left-hand side is just minus rho gamma plus gamma vj. I have no idea why there's a prime here. There should be no prime there. Is this correct? That equation holds. So what we explicitly show now is that if you make the assumption that A transforms as a Lorentz, as a four-vector via Lorentz transform, and you start with an equation that you know holds, you end up with an equation that holds. So the assumption is correct. mu really is a four-vector. It's much more elaborate this way than we did it before, yes? Same conclusion. Give me one more this time, and then break. But This takes an enormous amount of time, doesn't it? Man. Let's reserve this amount of space for the same argument a lot faster. Yeah. Because, let's start here again, our original starting point. Derivative with the primes. This. Let's Lorentz transform everything. Does this change on the Lorentz transform? No, it's a contraction of two four vectors. So I know immediately, we did it in full steps here, but I know immediately that this should be equal to the exact same thing without the primes. We do know how to transform this one. That was the thing that we did before as well. Gamma phi minus phi j1. There you go. Make this assumption. Squeeze it in here. And you can just read off that you get a left-hand side that really is equal to right-hand side. Is that too fast? Do you see what I mean? Same reasoning. This thing is contraction, so you can just remove the primes. This thing, I put my Lorentz transform information in. This thing, I assume that it transforms via Lorentz. So I plug this thing back in again, put it there, and I get the exact same equation as I do here. And there you're done. So, that should be a row, yes. It's A0, that's fine. Yeah, exactly. How about a break? So, life hack, pro tip. Make sure you get used to the mu notation, so you don't have to worry about all this crappy stuff all the time. Okay, so we've proven once more, a mu really does transform as a Lorentz transform, under a Lorentz transform, so a mu is a four vector. What we know, more and more extensively, we know that a mu is a four vector, so we know how it transforms. But that means, via these two rules, we can calculate how the e's and the b's are going to transform, because we know how the phi's and the a's transform on the Lorentz. So just plugging in the transformed version of the a's and the phi's in this one will give us a transformed version of the e's. Right? So we can just derive how these transform. I'm going to do one of them, because how many e's and b's do we have in components? How many components does E have, the electric field? 3. Now the B's also come with 3 components, so that means this is really 6 equations. And all of them transform in a somewhat different way. So it's quite a lot of work to do all 6 of them, so let's do one of them. And maybe we have time, we do a second one. I really advise you to go through these calculations, and the missing 4 you can do for yourself. Because ultimately what you will end up with is how the E's and the B's transform when they go from one system to another. Well, there's one immediate reason that I know that they're not going to transform as 4 vectors. And that is because the E field has only 3 components. It's hard to make a 4 vector out of 3 things. So it's not going to be a 4 vector. And B is also not going to be a 4 vector. So, well, it's going to find out what it is that they do. Well, you tell me, which one? EX, EY, EZ, BX, BY, BZ, I'm happy with all of them. Choose wisely. Notation wise.
If you want to choose.
No, I don't want to. Choose.
I don't mind. Then I'm choosing. Okay, sure. We're choosing BX.
Which one?
BX.
BX. Okay, come on, let's see if that was the wisest choice, but we'll see.
That was his choice.
It's fine, it's fine.
That's why I didn't choose it.
What would you have chosen?
I don't know. I didn't want to choose
I see, I notice a certain lack of
decision making.
Opinions.
of opinion on whether you like your E's or your B's.
Me specifically or?
No, people.
Oh, good.
Generally. I mean, everybody has a favorite component of a favorite field, right? I mean,
Yeah,
totally.
I
Of
happen to
course.
like EBY, I mean, but that's me, I'm a BY kind of guy. BX is what we're going to do. Okay, so how do you calculate BX given your A? It's on the board.
Just derivative of that.
No. Well, what kind, yeah, well, yes, there's a there's this one.
Curl.
Yeah, okay, there you go. Okay, so if I want to know Bx, what I need to do is take the rotation, or curl, which itself is a vector, not a 4 vector, a normal 3-dimensional vector. And of this thing, I have to take the x component. Agreed? Now, I want to know what it looks like in some other guy's coordinate system. So that's this.
Does the nabla have a needed prime as well?
Yes, because the nabla is derivatives with respect to x, y, and z in
Oh,
some
no,
complicated
yes,
manner.
Yes. That's it.
But is it your x, y, and z or the other guys? And we're transferring everything to the other guys, x, y, and z. So it comes with a nabla. And I have to take the x component of this. Well, let's remind ourselves first what a nabla does. The nabla of a vector is some complicated thing, yes. We've written it down many times before. I'll just remind myself what it is. This is the definition of rotation. Agreed? Of this, for our particular choice, we're going to take the x component. So we're only going to be interested in the x component of this thing, that's this thing. So I'm going to take the x component of this thing and write it here. So that's dy. You know this shorthand notation again, yes? This is just d dy. You okay, Scott? You look very saturated.
I'm okay.
Okay, good. So that's that. Oh, forgetting the primes, because remember, we're in the other guy's coordinate system. Again, remind yourself that there's a difference between a derivative with and without a prime. In one case, you're taking the derivative with respect to one guy's coordinates, and the other, you're taking the derivative with respect to the other guy's coordinates, so there's a difference there. Now, I want to know how my bx primed, which can be written as this, is related to the non-primed b's and or e's. Suggestions. What do I do? I want to get an expression without any, with some e's and b's, but without primes. What do I do?
The derivative y
Mm-hmm.
is the same as the other part,
Very good, yes.
and the same z and also a is
Good suggestion. Okay. Okay, I'm going to follow up on this. There's two things you have to Lorentz transform, the derivatives and the a's. Now, good comment here. For two observers moving in x direction with respect to each other, the y's and the z's do not change. So these derivatives you can just drop, not the derivatives, but the primes. Right? It's a good thing nobody chose by, which was my favorite, because by would have had a dx derivative with a prime, and that one does transform in a complicated way for people moving in x direction with respect to each other. So it was a good choice, actually. Yes.
I don't understand what, like, where we are dropping
It's my
is
choice.
the prime.
Ah.
Because like if you are just moving in x direction, should the derivative be 0 because it's constant?
I'm not sure why it should be 0. What is
I
constant
don't
here?
know, that's all I think. So,
Okay.
no?
Um,
Like since we are moving just in one direction,
Yes.
there's like no change in y.
there is no change in y, but you can still have a y derivative.
Okay, but since there's no change,
Let me give you an example. Okay? Suppose that I'm throwing my pen upwards,
Right.
and this is what I call my y direction. Okay? And you want to calculate how fast the pen is moving through space in y direction. Now, there you go. You've done the measurement and you got some number for y. Okay? I'm going to do the same experiment now, but now in y prime, in a prime system. There we go.
Oh, okay.
Is the y now
Yeah,
different?
yeah.
It's the same thing.
Yeah, yes.
Okay. So this is what I'm saying. My y prime really is y, and the z prime is. The x isn't because of Lorentz contraction, difficult stuff and such. But fortunately, there's only x primed here. So my choice would have been this one. I think would have been more complicated. But good, good, good. How do these transform? You say the same? Remember, we've proven many times over that A itself, A mu, is a 4 vector. So that means that A prime 0 is gamma A0 minus V A1, and that A1 prime is gamma A1 minus V A0. Agreed? Now, if you're moving in x direction with respect to each other, A2 prime is the same as A2, and A3 prime is the same as A3. What happens? It's the same. You can drop these as well. A2, or excuse me, A3 is A prime 3. So we were extremely fortunate in this particular case. Do not take this as a general rule that all the primes could easily be dropped. And what I think that we have here is, isn't this just the x component of this thing, but now without the primes? This, without the primes. And this thing we recognize as B. Conclusion, one guy's magnetic field in x direction is exactly the same as the other guy's magnetic field in x direction. Well, that's easy. Life would have been good if that would hold for all 6 components. But trust me, we just happen to have picked a lucky one. Okay, let's do one more. Suggestions. And don't try to pick one that happens to say the same, okay? E, which one?
EX.
Yeah, no, I don't think it works for EX.
I don't think it works for
Probably
EX.
not.
Nah,
Easy.
Oh, then choose
EZ, I hear EZ. Anything else? Let's go for EZ.
It's not many left.
Let's see if it's easy.
Yeah.
Yeah, okay. Yeah,
Is
that's.
that why you chose it? Okay.
Yeah, hilarious.
That's gonna get you so many views on YouTube.
I think so. Yes, that joke alone.
Yeah.
Subscribe. Just for one.
Okay, good.
Yeah.
Okay, so we have found one particular rule. We need 6 of them to complete everything, to connect all the B's to all the E's for the 2 observers. One we have found. Bx primed is the same as Bx. Okay, good. Next one was EZ. EZ primed. Now, according to what we've derived in the first 2 lectures, that's this expression. So it's minus the gradient of phi, but in the prime system. That guy's phi in his derivatives. Now, the gradient gives you a vector, and you have to have the z component of that vector. This is just d z part. No physics, it's just knowing by heart what a gradient is in z direction. Minus the ddt, be careful, ddt primed of A. Which A? 3 components. It's a vector.
Z.
The Z component, but with a prime. So there you go. And now do our favorite trick, do some Lorentz transforms. More difficult in this particular case. Oh, not this one though, because DDZ primes is DDZ again.
Yeah.
Good, good, good. Okay, great. We can drop that one. This one still has a prime, and unfortunately the time derivative also comes with a prime. So that's that. So another. Minutes ago, we should be able to figure this out. This one? That's Lorentz transform this one. Okay, here's the rub again. It's a 4 vector, but it's a contravariant 4 vector, so it goes with the opposite derivative. Yeah, so let's leave the first term alone for now. This one. So what should it become? DDT prime? There's a gamma, I agree. Okay.
Plus.
Exactly, plus. That's the rub here. Should be this. Okay, we have replaced all our derivatives now with the on prime one. Yes.
It's not in the Z.
Which one?
Like plus V derived.
Nee, sorry, no.
Yeah. I said because we move along. Yeah.
Yes, that's the reason. Yes. I have no idea where that came from.
You can also do it in Dutch.
Sorry?
You can also do it in Dutch today.
I guess, well,
Sure.
we would leave out a couple of people, I think.
You.
Yes, I'm sure not everybody here speaks Dutch.
Helaas.
Exactly. Domme.
Yes, the meisje.
We should do it next time.
Oh yeah, sure.
Okay, okay, these derivatives are now fine. Okay, those we have replaced by the non-prime versions. We now have to replace these. Now, how does AZ change from one person to the next? Same? Same. Exactly, because the Lorentz transform leaves the Z components alone. So, okay, we can drop this prime. This one is completely done now. Everything is unprimed. This one?
Isn't that A prime 0?
This one?
Yes.
Yes, there's A prime
Yeah,
0.
so it's yeah,
It's
that
this
one.
Yeah,
That's all.
exactly, yes. Yeah, phi is what we call A0.
And yeah, the 5 prime is then A
Yes,
prime.
exactly, yes. Well, yeah, we can use this Lorentz transform for that one. So that gives us gamma times A0 minus phi A1. And look how beautifully we've gotten rid of all of our primes now. This is a 1, it's not a let's work on the derivatives for a second. Does the derivative feel gamma and or V? No. Move with constant velocity with respect to each other, the two observers. If not, if some happen to be moving with an acceleration with respect to the other one, that means that one of them is not an inertial frame. And we're sticking to inertial frames for now. So that means that the gamma and the V go outside of the integration. And if I'm not mistaken, that should give us this. AZ, we'll call A3, minus gamma V. So I'm getting this. Oh, excuse me, this is A3. So I'm getting this. Ah, okay. Now what? We've gotten rid of all of our primes. Everything is now written in the other guy's coordinate system. The last thing we have to do, remember we were trying to figure out how the E's and the B's are connected to the other guy's E's and B's. What we've now done is connected one guy's E to the other guy's A and phi. We don't want connection to A and phi, we want connection to the other guy's E and B. So let's see if we can write this in terms of E's and B's.
DZ.
Which one? Where?
It's minus DC phi dash.
This one?
Two lines above. Then we go down.
Oh. Uh-huh.
It's supposed to be DC instead of D.
Yes. Excuse me, everybody. My bad. This is DZ. And for some reason, I read it as a T when I copied it to the next line. These are still DZs. I was getting worried when I was looking at the expression. I thought, wait a minute, something is off here. But thank you. It's my crappy copying. These are all DZs. So this is a DZ and that is a DZ. But you have saved me a lot of time and frustration and embarrassment now. So good, good, good. Okay, but the question still remains. Can we write what we found now in terms of E's and B's? Maybe it helps if I underline something very suggestively. Maybe underline something else very suggestively.
Oh, okay.
Yeah, so what is
Yeah, so you take those. Wait.
It's gamma E.
but which E? Which component?
Set.
EZ here you can write as minus ddz of phi minus daz dt, which are exactly these terms here. Maybe there's some confusion because it's a0 here and I call it phi over there, but that was the same thing, isn't it? So these two together via this rule are exactly EZ, but now with a gamma in front. Apparently this is what happens. I still have two remaining terms.
So I didn't really.
Okay, good, good, good. Sure. Do you see that there is a dz of a0 here?
Yeah.
Okay, well a0 is a different label for phi.
Okay.
So what I have here is minus, forget about the gammas for a second, you have minus ddz of phi, minus, forget about the gamma, the daz dt. That's exactly this thing, the z component of this rule. So what I found in my expression here, the two ones with the blue underscore, this one, forget about the gamma for a second.
Yeah.
This one is that one, and this one is that one. Now these two together is the same thing as E,
Yeah.
and that's what I did here. And the only thing I did was to put the gamma in front because both of them had a gamma now. I still have two remaining terms though. I have gamma V these two terms, the remaining ones, I've written like this. The one I've replaced by X and the 3 by Z. But it looks like this.
So it's like the second term up there, and the
This one?
curl of A, yeah? So
Yeah.
it's a B,
That's right.
yeah?
Which B? Which component?
Y component?
Yes. This is By.
Shit.
And this is where we want it to be. Because what we found now that if you take my electric field the Z direction, and you happen to be moving with constant velocity v in x direction with respect to me, then you don't see just an EZ, you see a gamma EZ plus a gamma V By. You see a magnetic field where I don't. and this is the answer to your question, what the geometrical interpretation is of the Lorentz transforms in for the scalar and the vector field. It tells you how much E is transferred into B of the other guy.
Okay, so the prime is not moving and the other one is moving.
They're moving with respect to each other.
Back to each other?
Yes.
Oh, okay.
And which one is at rest and which one is not at rest is a non-valid question of relativity. The only thing you know is that they're moving with respect to each other. Now we have something important here because we've also now found the rule for EZs. Gamma EZ plus gamma VBY. There you go. Yes?
Don't we have some kind of paradox here? Like some thought experiment where someone has like a magnetic field and the other one doesn't?
Yes.
And for example, let's put a needle in it and we know that needles can be deviated by a magnetic field. So the one sees the needle moving and the other one doesn't?
Yes. You won't have that issue for the following reason. It's a good question. Can you think, what we have now is that one guy's electric field, my EZ, is your EZ with a gamma plus a little bit of magnetic field all of a sudden, and that sounds strange. My claim is both of them will get the same experimental predictions for this, and the reason is as follows. Always taking you as an example. He's a needle, right? You said a needle in an electric field, and forget about the directions for a second. Just the general idea. He's a needle with a certain amount of charge push into that thing. I see his needle pointing up. That's his EZ or something like that.
Mm-hmm.
This general idea. Now I come walking past. For one thing, what I see happening is that he is now Lorentz contracted with respect to me. Right? This is what happens if you move with respect to something else. But that means that the amount of charge density, his rho, has gone up. Because there's less space, as far as I can see, but there's the same amount of charge. So his charge density has gone up. So that means that the way that I see his electric field is a lot bigger now. Which is exactly what I see here. Because the electric field has now gone up with a factor of gamma, depending on how fast I was moving. There's also a magnetic field. Now if I were to have a magnet in my hand, and I were to measure something, if I were standing still with the magnet in my hand, it will not feel chi. Why? Because there's no moving charges. But now when I am moving, his charge is now a moving charge, so for the magnet all of a sudden it feels like there is a magnetic field. That's this term. So it's completely understandable why it looks like this. His electric field has gone up because there's the same amount of charge in a smaller space because of Lorentz contraction, and because there's now a moving charge in my frame, in my inertial frame, I also see a magnetic field. And that's what you have here.
Okay, but if suppose you will put the needle in his reference frame,
Yes.
and you go by and you see that there's a magnetic field, so you should have to see the needle start deviating, but in this reference there's like no magnetic field.
Yes, but the amount of magnetic field that I am not seeing
Yeah.
is mopped up by the amount of electric fields from the other guy. You know what you can compare this to? I'm not really sure. I mean, that is the answer to your question, but
Yeah, well, my question is like, is it
Yes.
moving or not?
that question is not valid in relativity. No, this is not a dodge. No, this is really true. If the question is something moving in special relativity, then you say that apparently there is some frame from which you can determine whether you're moving or not. Some rest frame, that if you want to know if you're moving, you have to look at that frame. If you're moving with respect to that frame, then you're moving. So you're sort of singling out that there is one particular frame that is taken as the frame that you use to determine whether you're moving or not. An absolute rest frame is what this is called. That thing does not exist. And that's exactly the idea of spatial relativity, that all inertial observers should be able to use the same rules. At the moment that you say, well, but this guy is in a special frame because his frame is the reference frame with which we determine whether things are moving, you're breaking the idea that everybody has the same laws of physics. The best thing you can do in spatial relativity is say, if you're moving with respect to each other. Not if something is absolutely standing still. I'm sorry, this is the shortest answer I can give.
So would the needle be moving for chai?
In which we have to be very careful about the setup. What is the setup exactly?
What you described before that you were passing by and
So he's here, he has a needle,
Mhm.
okay? Thing is not moving, but it does have an electric field. And I come walking by, yes, in my frame this needle is moving. Why? Not because the needle is moving with respect to chai, but in my frame, suppose the needle is pointed like this, I see that it is moving, isn't it? The needle is pointing towards the wall, this dot over here. Right, this is your needle sticking that way. I come walking past, but in my frame, I see that the thing is constantly turning to that thing, so as compared to me, that thing is moving in that direction. So there's now a movement of the needle in my frame.
So in your frame, your conclusion would be that the needle is moving because of a magnetic field.
Yes.
Right.
But both of us, me saying, well, the needle moves because of the electric field the magnetic field that I see now, or Chai saying there's no magnetic field, my needle is not moving, even though I say there's a magnetic field and the needle is moving, and he says, no, there's no magnetic field and the needle is not moving, both of us agree that the needle is pointing towards that dot on the wall. That has not changed.